Okay, so today we're going to continue talking about energy.
Stop.
If you guys could just be like a little extra like focused today, just because like I'm kind of like on edge already because I don't feel good. So just help me out there. I don't want to freak out, but I have a feeling of freaking out is going to happen just because I'm a sinner. So it helps me to like be open in how I feel, just so that like I'm aware before I do it. If that makes sense. Does that make sense? Doesn't help. Not helping.
Mr. Kramer has a feeling.
Oh, I guess Kramer from Seinfeld.
Well, I can still do it for twin day. Anybody want a twin with me?
I am.
I
am so do that.
Wait,
I've already dipped it.
Okay, how do I
Just
how does that
dress him
work?
as
You come
yourself.
as him.
I come as you?
As me?
Yeah, bring a like a.
Wait, so is that how that works, or?
Bald cap.
Well, I'm just dressing up in
Inside,
like,
Mr. Fisher.
like loose khakis, a plaid
Whoa.
shirt, and then wearing like some hat.
You
and
can
then
both
rubber
wear the
face.
same thing. It's like 5 times.
I
So
know.
then-
Last you know, dress up like.
I had to get one of them like swimmer
I think
things
it's
to put on my head, and then like get some sort of like really suction
tape on the
thing.
tail.
No, I'll put my
Plunger.
plunger on my head and then wrap it in hair.
Then you have to wear tight pants.
Own tight pants. Is this count as tight pants?
Yeah.
Yeah, wear it up.
I said that you have to close yourself. And wear leggings.
Hey, Craig,
Hey, when do we get
let's
these
wear
t-shirts?
leggings and short running shorts.
No, when do we get
Leggings and short running shorts?
Yeah,
I'd probably do that.
like short running shorts.
Sure.
We've never had these before.
I could, I was gonna say, I won't fit.
Can I wear leggings too?
And you're right.
I'm not gonna wear my leggings
Let's triplet.
I can't wear this.
I do fit into my wife.
Wow.
Back up.
Alright, okay. So I thought, so twinning is you just act like the other person.
Well, you have to say or. You can, or you can do like characters that go
I'm
together.
trying to think. I'll have to shave everything but this little bit here.
Shaggy.
Should I do that? I should do that. I look really bad though. I look like Isaiah.
Like shave everything. I'm right here.
That's why I keep it
Kramer,
short.
get that baby face going.
Cole.
Or
It's just, I have a friend that told me never to fully shave
Cole.
because I just
shake Craig's fully
It's
shaved.
scary.
well, all but this.
Neck beard.
Keep his next.
Kramer, keep
That's
that
all
neck
you
beard
should
going.
make sure you.
That's literally how
it
that's
is.
literally how it is.
It's like,
No, I'm
Okay.
He's dressing up. Yeah.
We are.
I'm gonna be so
Meanwhile.
So what are we gonna do?
Okay, so we are going to talk about the other type of energy pertinent to physics, and that's going to be potential energy. We talked about kinetic energy yesterday. What was kinetic energy?
Movement and motion.
Movement, energy. What two variables did it depend upon?
Speed, mass and velocity.
Mass and velocity, or mass and speed. Okay, it's probably speed, just because it's a scalar quantity. Kinetic energy is. What variable was more impacting for kinetic energy? Or had a greater impact?
Velocity.
Why?
Because
Because
it's
it's
square.
squared. Okay. So we're going to talk about potential energy today. There are 2 types of potential energies. There's actually more than 2 types, but we're only going to do 2 types.
Isn't it nuclear?
Yeah, but
Yeah, I can talk about that one.
there's nuclear, there's electric, there's magnetic, there's chemical, okay? So, unlike kinetic energy, however, potential energy depends not only on the properties of the object, but also on the object's interactions with its environment. So kinetic energy is like solely based upon what the object's doing. Potential energy is that plus how things around it are acting on it. Okay? So, very first one we'll talk about, is your gravitational potential energy, and that should say PEG, not PEA.
Mine says it says G on the note.
Does it? Okay. And you should recall this particular equation. You should find a different job when a student thinks that's more important than what you have to say.
Oh.
It's not, it's only cool.
That's so embarrassing.
I don't know who's more embarrassed, me or I should be more embarrassed. Okay. Potential energy due to gravity. Ouch. Do you remember this equation from physical science? You don't.
I was typing it in my
That's what science was like.
Isaac probably knows.
Okay? Potential energy due to gravity depends on 3 variables. Now, really, it only depends on. The only one that's really important is one of them, and I remember physical
Oh, I'm
science.
so mad about this. Oh, I remember this. I got it wrong on a quiz and I got so mad. Because I put mass instead of height. Because it's stupid, because multiplication is all the same.
No, mass can't change. Anyways, mass times G, what's G? What is G?
9.81.
9.81. Okay? Now that is not negative 9.81, that's the magnitude of gravity. G is just the magnitude of gravity, so the mass times 9.81 times the height, and the height depends on 0 level.
Sea
Is
level?
this a note card
0
equation?
Absolutely.
Is that just sea level?
0 level can be whatever you want it to be.
What?
Anything?
But then wouldn't it change?
Yes. Well, let me explain. Say we got some sort of building. We got a ball that is falling off of it and landing here. Somehow it's going to do that. Inertia doesn't apply. Momentum not applied. Okay, so let's say that the distance here from the ground to that is 3 meters, and this is 6 meters. I will say this. Almost always is it best for you to choose your 0 level as the ground. I would say 99.9% of the time that's usually the best. Okay? It also depends on what it's asking you. If it was asking you what is the potential energy at this position, I would choose the 0 level to be the ground. But if it says what is the change in potential energy from here to here, I would probably set this as 0 and make this 3. Any idea why?
Well, then I'll do one time.
Because I only have to do it once, I don't have to do it twice. Here's what I mean. If I wanted to find the change in potential energy, I'd have to do this with a height of 3, and then this again with a height of 6, and find the difference. That make sense? That's how you would find the change in potential energy between here and here.
How do you choose that one as a 0?
If I choose this as 0, because the difference is still 3, regardless if it's between 0 and 3 and 3 and 6. The difference is still 3 in height, right?
So you
Are you guys paying attention? Come on. So, by choosing this is the 0 level for this particular situation, I know that the potential energy here would be 0, and I can just use 3 as this and do it once instead of having to do 2 equations. Does that make sense? Now, there isn't a ton of situations where it would make a lot of logical sense for you to choose 0 level to be something not the ground, but there are some situations. 99.9% of the time, 0 level probably should be the what?
Ground.
Okay?
And also the height of 6 has greater.
The 3? Yeah. But in that case, notice I said we're solving for the change of potential energy.
No, I was just saying in general.
Yeah. Okay. All right. Elastic potential energy. This is the other type of potential energy. I didn't state from the previous section. What do you think the potential energy unit is? Joules. Okay? Also, that MGH equation really only works if you're assuming constant acceleration due to gravity. So we're again assuming we're in a vacuum. Okay? Because technically,
I like that.
really sick. Technically, even though it's so small, the gravity acting on this here and the gravity acting on this here is really different.
Yeah, that's what I was asking you about the sea level thing. It's like gravity on top of the mountain is different than.
Yes. And so this really only works if you assume that there's no difference in gravity between the ground and the mountain. Okay? Yes?
Is that square, that's open to the x, right?
Yep.
And what did you say case stood for?
I haven't even talked about that. Where was I? Joules is unit potential energy, and you gotta assume that gravity's acceleration is constant. And no air resistance, because if you had air resistance, your acceleration would change too, wouldn't it? Okay. All right. So electric potential energy, 1/2 kx squared. So let me explain what the difference between K, or what K is. K is really an experimentally determined constant that has everything to do with
A spring.
how stiff the spring is.
You don't keep planets in orbit around the spring. I watched a video about people used to think that like planets just went up and down around the sun because like how it goes to us.
With their spring.
So it's more because like orbit, so it's like just going up and down. Well, I watched a good minute because he's on.
Boy.
Just be careful when you stretch it, don't like overstretch it.
I'm gonna break it. Don't worry.
Okay? You know what's the difference between those two?
Oh.
They're not the same. Okay, so I'm going to pass you around two springs that almost look identical, but they have a different spring constant. Okay, this one has a 15 Newton per meter spring constant. This has a 5 Newton per meter spring constant. All that simply means is one is 3 times harder to stretch or to compress. That's what the K really tells you, how stiff the spring is.
Well, how can you make one less springy than the other?
Less tension.
How the spring's made, I don't know exactly.
Wouldn't it matter how many times it's like going around?
Probably coil.
That has something to do with it, but if I look at it, I don't. Oh yeah, it does look like the one's coiled more. Yeah, and so if it's coiled more, it's probably not as thick either.
Wait,
I thought it'd be a bullet when we had more tension, or whatever it's called.
Well, I
Be
think-
harder to pull.
I think
I think it's the opposite.
No, the figure one was harder to pull.
Yeah, I think it's the opposite.
As in the one.
Because like if you think of a huge thick
This one more
spring,
coils easier to pull.
Huge, thick spring.
just one big base spring.
Yeah, that's actually not just an opposite.
One big wet noodle.
This one has less.
Yeah, the thicker is harder to pull.
So this one, yeah.
I think if you were to actually look at this,
Is it because it's probably harder to make more material for it to distribute?
Probably. I don't know for sure, but. Okay, so I want you to pass those around. Please don't stretch them really. I don't know how to say it.
Don't be a mean.
Don't be a meanie to the springy. Okay? So I'm just going to show you an example of the difference between two springs that look very similar, but one is more difficult to move. What?
the thinker's harder.
Okay? Okay, so what is X then? That's another thing that we probably need to understand here. X is the distance compressed or stretched. Okay, what does that mean?
Is that like displacement? Like
From its starting.
Yeah, I go from starting to.
So what X is going to be here is the distance from your relaxed state to your either stretched state or your compressed state.
Well, those ones, these ones you can't really.
Those ones you can't? Well, yeah, because they're right next to each other. But you've seen those springs that have more space in between them that you can compress?
Yeah,
So it's like a mattress.
Okay?
Yep.
So, here's kind of what this would look like. What this is showing you from here to here would be the distance of the spring if it were in its relaxed state or at equilibrium, where there is no compressing or stretching of the spring. Okay?
So you have to leave us the constant, right? For each-
Yes, you'll have either that or you'll have to solve for it. Okay? Now, here it's compressed. So x is not this distance, but pay attention here. X is not this distance, it's this distance.
Oh.
It's not how long the spring is when it's compressed, it's the difference between its relaxed state and its compressed state, or its relaxed state and whatever you stretch it to. Okay? It's the difference from equilibrium. It's not what it's currently at, it's your difference from equilibrium. So let's say I said the spring was 20 centimeters relaxed. I compress it to 5 centimeters. What's your x? 15. If I stretched it to 50 centimeters, what's your x? 30.
Oh, wow.
This is the relaxed state.
I wasn't too.
Oh.
Okay? So it's how much you either are stretched from your relaxed state or how much you're compressed from your relaxed state. Yes?
It would be negative this distance, right? Because like if it started at 20 and you stretched it to 50, is it 20 minus 50?
No, Jules, is Jules scaling? Jules is scaling, right?
Is it like a
I'm guessing it doesn't matter.
Either way, because
I try to remember.
Well, it's squared.
It's squared, so it doesn't matter.
So
No matter what you do,
relaxed.
That's true.
Negative.
Yeah.
And you have negative energy?
Mr. Kramer,
But
so you're taking the relaxed spring and then subtracting the compressed to find
it's
the.
the difference. It's always the difference, but be careful because if I stretch it, it's not 20 minus 50, it's 50 minus 20. Does that make sense?
Which one's 50, which one's 20?
So if I'm saying this is relaxed, okay, and this would be compressed, and let's say I stretched it, a different situation, to 50. So here it's 20 minus 5, but here it'd be 50 minus 20. It's the difference between your relaxed state and your either stretched state, or your relaxed state and your
So absolutely.
yeah, I mean, that's how I would do it since it's squared anyways. I'm sure there's a sine component in it, but with the fact that it's squared doesn't change anything, yeah?
Is the equation 1/2 kx squared?
Yes, I think, right?
So you
Yeah.
always do the end result minus where it started?
Yeah, but it was on the wrong.
Whether even.
No, because this is the end result and you wouldn't do 5 minus 20. It's the difference between how I would get from my relaxed to my stretched. 30, 15, minus 15.
It's just the difference in between.
Yeah, absolutely.
As you're walking.
Absolute
How far would you
value. Okay.
walk? What?
Okay.
And if you're a spring, you might walk.
Okay, let's do a problem.
How far would you walk?
This is a good problem.
Long words.
Lot of words, lots of stuff. Are we down with the springs yet?
80% of it's plus.
One of the
Are you
differences.
still playing with the spring back there? That's
yes,
too much
yes,
stress.
he has it.
Oh, that's
That's
not
a
spring.
rover.
I was like, you're stretching my spring that much? Okay, go crazy.
That's why I tried to do this. Oh, I'm not
Where is it?
This is what I tried to do.
One of the distance between,
The spring break.
the difference between the distance compressed and relaxed state would be equal to. Oh, whoa!
The spring break.
Oh, nice! Like the difference between relaxed and compressed, wouldn't that be equal to?
You're talking about max stretch and compress? Yes, the maximum you can stretch or compress something is the same, but I can have varying levels of how much I stretch or compress it.
Because on this one, it shows the relaxed length is like a certain size.
Uh-huh.
So then if you took the relaxed length and then take away the distance compressed, then you get the distance. I'm
I
lost.
think you're overthinking this. It's really just the difference between your initial and your final.
Yeah, absolutely. How are
Yeah.
these both compressed? Oh no, this is when you compress it.
This is what the spring looks like if it's compressed. This is the spring if it were, like, this block
This is
wasn't
how
there.
much it moved before it was compressed.
Yeah, that's how much it moved to get compressed.
So that's the original.
So I was looking at these all wrong. I thought this was stretched, this was compressed, and this was relaxed.
No, this whole length here would be what its relaxed length would be. From here to here would be its relaxed length.
Honestly,
Okay? This is the distance I had to go to compress it to this.
I thought this was saying compressed. I mean, this was saying stretched, and the other one was compressed.
Okay? Let's do this particular problem. Kind of a fun little unique guy here. We got a 70 kilogram stuntman. Is attached to a bungee cord. Okay, so we know the unstretched length of the bungee cord. I'm not going to write that down because we'll get that here in a sec. He jumps off a bridge spanning a river from a height of 50 meters. When he finally stops, the cord has stretched a length of 44 meters. Treat the stuntman as a point mass, disregard the weight of the bungee cord. Assuming the spring constant, what is the total potential energy relative to the water? So we're saying the waters are zero level when the man stops. So let's say we got a bridge here. We got a dude looking on, and there's a bungee cord, and let's say, I don't want to show like the difference between relaxed and stretched. Okay, let's say the relaxed length is 15 meters. That's just the length of the bungee cord, right? Not stretched, not compressed, nothing. Okay, the guy gets on it, and it stretches to a distance of 44 meters. And we also know the water here, or the distance between the bridge and my ground, or water, or I'm assuming he's not doing bungee jumping over a solid ground, but maybe, idiot. So height is that, but that's not the height we want. Okay, so we want to know the potential energy here. Okay? We want to know the potential energy when he stops. So assuming they're not saying they're not saying he bungees a bunch of times and then comes to a stop. We're saying he comes and he stretches, and at the very bottom where he would stop his motion before going back up, what is his potential energy there? Yes?
why do we need the 50 meters if we can just roll out?
I'll show you.
Kramer, what's the difference between 15 and 44? What did you, why?
Relaxed.
So, okay, so that's when it falls before it stretches.
That's just the length of the bungee cord. Yeah, that's not compressed.
Okay.
Okay?
Wait, it's still asking for elapsed potential.
It wants total potential energy. So that would include, there's gravitational potential energy, isn't there? In this particular situation?
Yeah. So then you subtract it.
This is after there.
Add them together. Plus elastic potential energy.
So then your answer.
Okay? So we gotta figure out here, let's talk about potential energy. This is MGH. We know the M, right?
Yeah.
What is it?
70.
We know the G, right?
Yeah. It is 9.1.
What is the height?
The height is 6 meters.
Okay, the height is 6. Why is it 6?
So 50 from where he is in the water.
Where is my position relative to the ground right now?
6 meters.
6 meters, right? I know that on the bungee cord it's stretched to 44 meters, and I know the distance from the bridge to the ground was 50. So shouldn't my height at this location here be 6 meters above the ground?
We're doing gravity right now, right?
Yep.
Oh.
Yeah.
Everyone see that?
Yeah.
So 6 is the height.
Yes.
So you
potential-
take how far you fell versus how much it is to reach the bottom. And
Yeah, I want to know, basically, when you're doing potential energy gravity, your H should be, or your height should be the distance above your zero level. Or zero level is the ground.
Okay.
how far are we above zero level?
So it's not how far you stretched.
No, we're not talking about elastic yet. We're talking potential energy due to gravity. This is the elastic. We'll do that in a second. Okay?
That doesn't make sense. How is that all 50 and that part 15, that part 44? And you're
I'm not saying it's 15 plus 44. I'm saying the distance from here to here is 44.
Oh. Oh. Okay.
Okay? So it should be 6. Okay, plus 1/2. Do we know the K?
Yes.
So 0.8. I just given
Multiply by
the K.
29.
Oh, that's the constant.
Okay, multiplied by a number squared. The question is, what is my X? It is 29. Why is it 29?
Because it's
Stretch minus relax.
stretch minus relax. Question though.
Yeah.
The forces are in different directions, so they cancel out. So it's has to be balanced.
We're not finding
No,
force
it's
here.
Yeah,
We're
but
finding
potential
potential.
energy, like the gravity, potential energy, and the elastic go in different directions.
It's a scale,
Right or no?
So you're always gonna subtract your relaxed.
Because the spring wants to come back and the gravity wants to pull you down.
Sure.
So they equal out or no?
But I'm just asking at that point, how much potential energy do I have? I know it's in opposite directions. I see what you're saying.
Okay.
But at that point, what is the total potential energy? Yeah, I get what you're saying. I suppose you could, if I wanted to know like the net difference, they would ask you that. Most of the time, they just want to know at that point.
Also, why don't we use negative 9.1?
Because it's just magnitude.
Is K always meters per meter?
Yeah. So does everyone understand why your X in this case
44 minus 15.
is 29? Because remember, definition of X is how much you're stretched or how much you were compressed away from your original relaxed state. So my original relaxed state is here. I only really stretched from here to here, didn't I?
Yeah.
Make sense?
Yeah.
Why did you use the distance left over instead of the distance that's used up?
What,
Like instead of 44, you use 6. Because that's what's left.
44. Oh, because, so potential energy due to gravity, or how much gravity potential energy you have, is based upon how high or how much you are above zero level, which our zero level is the ground. Well, how far above the ground are we? 6 meters. Does that make sense? Okay? And it will always be distance between your zero level and where you're at. Will always be your height. Okay? What do we get when we plug this into our calculator?
34,000
34,000.
10 to the 4
Can I write this in scientific notation?
times 10 to
I suppose.
the 4. What? Okay, the labor is Jew. Labor.
Let's go! Cole, let's go.
The lava is Jew.
You were looking up your grades? That's more valuable than me speaking in class, Bryce?